Hello once again, ladies and gentlemen. Welcome back. We're on to question number 24 on the 2000 grade 8 Gauss. So let's take a look. Question number 24. It's about an equilateral triangle. So an equilateral triangle ABC, line segments are drawn from a point P to the vertices A, B, and C to form three identical triangles. So APB, APC, and BPC. The points D, E, and F are the midpoints of the three sides, and they are joined as shown in the diagram. So we connect the midpoints up to one another. What fraction of ABC is shaded? Okay. So for this sort of question, I like to stop and say, okay, well, we've got sort of two things going on. We've got the P and its lines, and then we've got the D, E, and F. So let's say we just take them away, and take one set of our construction away. So let's take away D, E, F, and take a look at A, P, B, and C. So we'll just draw that. We'll draw in D, E, F later, or maybe we'll look at D, E, F by themselves again later. So we have a point P here, and P in the middle gives us A, B, C, and P. And we know that these guys are identical. Okay? So, when it comes to being identical, we have a couple options. I mean, are they identical with flips? So, for example, if I know that they're identical in that this line segment is the same as this line, so this line segment on APB, or APC, is the same as this line segment down here on BPC, well, then that really means that APC is isosceles, and so this line segment is also the same. So that could certainly happen, but suppose instead, let's get our triangle back. Suppose it's not that way. Suppose that APC is just sort of flipped over to make ABP. Okay? So those guys are identical. Well, that still means that one of BP or PC has to be the same as this line segment because BPC is still identical to APC. So either this line segment over here or this line segment over here is equal. And then we still get one of these triangles is isosceles, so they've all got to be isosceles. So it's pretty quick to see that they're all isosceles. And so actually we'll keep the blue. So from there, our interior angle of 60 degrees becomes two identical interior angles of 30 degrees. Okay, so that's pretty interesting and useful information. So P splits them, the distance PA, PB, and PC, these are equal. So that's something we've learned. So these guys are equal. And we've also learned a little something about the angles. So angle ACP is equal to angle CAP is equal to angle BAP is equal to angle ABP, angle equal to angle BCP equal to angle CBP, and it's equal to 30 degrees. Okay, and so that another way to see that would be, well, this interior angle's got to be the same for each of the triangles. So APC is going to be same as APB, and same as angle BPC, and together they have to make up 360, so we divide by 3, we get 120 degrees. So there's lots of different ways, and now we know all the angles. Okay, so that's pretty useful information. We broke our construction down a little bit. Now, instead of looking at what P gives us, how about we look at what DEF gives us? A, C, B, and I think it was D was over here, E, and F. Okay, we'll use red when we mark up this one. So, what do we know? Well, we know that this here is 60 degrees, and this here is 60 degrees, and this here is 60 degrees. And we also know that since it's equilateral, we know that AC is equal to BC is equal to BC. And since D, E, and F are midpoints, we can see pretty quickly that DA is equal to DB is equal to EA is equal to EC is equal to FB is equal to FC is equal to 1/2 AB, 1/2 BC, 1/2 CA. So all of these lengths here are equal, and they're both a half of the side length that we have beforehand. So now we have DBF is isosceles. So this angle is the same as this angle, and this angle is the same as this angle, and this angle is the same as this angle. But the other angle is 60, which means that those two have to add up to 120. So each of these triangles is going to have the other two angles as 60 degrees. So ADE, BDF, and CEF, well, they're all equilateral. And if they're equilateral, then that means that this third side length is equal, and therefore DEF is also equilateral, and they're all congruent. Equilateral. So ADE is congruent to DEF, because they all have the same side length and they're all equilateral. So they're going to be similar, and with the same side length, they must be congruent. They must be the exact same triangle, just moved around. Okay. So that's what happens when we look at both cases individually. We get a whole ton of information that now we can apply, oh geez, that's awful, to the big picture. We get A, we get B, we get C, we get D, F, E, and now we add in point P. Okay. And we'll actually put P over here. And we're asked about the shaded region here. Okay. Well, let's choose, I don't know, the purple. So we know that this is 30, and we know that this is 60, and therefore we have a 90-degree angle right here. Okay? And this over here being 30, this is 60, still have our 90-degree angle here. So one of the things that I can notice is that this over here, the shaded region right here, is going to be 1/2 of triangle ADE. Okay, it's going to be exactly 1/2. It's a ratio of 2 to 1 on the side lengths of a 30, 60, 90 triangle. So 2 to 1. So this is 1 and this is 2. So it's going to be, we have the same height, but now half of a triangle. So that's the idea there. So part of our shaded region is going to be a half of one of these smaller equilateral triangles. Okay. Now let's take a look. This is 60. We know we have right angles here. And we know that each of these interior angles is 120. And this fellow here is 60. And this length and this length are going to be equal. Turns out P splits this up into thirds. So AP, BP, and PC, or CP, I guess, they split DEF into thirds. So this is 1/3 of triangle DEF. Okay. But triangle ADE is congruent to DEF. Shaded area is 1/3 of DEF plus 1/2 of DEF. And let's switch back to black. So we can flip that over and take a look at it the other side. 1/2 plus 1/3. Why is my page not flipping? There we go. 1/2 plus 1/3. That's 5/6. So that's 5/6 of triangle DEF. Okay, that's great. Now we know the shaded area. We want to figure out how much of it is how much of ABC is that shaded area. Well, ABC, we showed that it's made up of these 4 equilateral congruent triangles, one of which is DEF. So the shaded area is 3/6 of DEF. Triangle ABC is 4 copies of DEF. So the shaded area over the total size of ABC, so that way we can figure out how much of it, what fraction of it is 5/6 of DEF over 4 copies of DEF. The DEFs are going to cancel, and we're going to be left with 5/24, which I believe was A or B. I think it was B. Yeah, there it is, B. All right. So that's what happens. We had a very interesting but ultimately confusing construction because there was a lot going on with D, E, and F and P all together. So what did we do? We stopped for a moment and we said, okay, what happens when we just add that P in? And what happens when we add in D and F and connect them up separately? And we said, what can we figure out there? And once we combined them, we didn't have to be a little unsure about what we were doing. We already knew some things like this is going to be an angle of 30 degrees. These are 60 degrees. So we get a 30, 60, 90 triangle in here. We can see by a symmetry argument that P splits DEF up into thirds. And we can keep going like that. So I think overall that was a very nice question. And we got just one more to go. Question 25. We'll take a look at that in the very next video. So as usual, thank you guys so much for watching, and I'll see you as we finish up the paper in the very next video.